Hello everyone. In this video we are going to discuss metric spaces. Now, a definition of the metric space is set X whose elements we shall call points is said to be a metric space if with any 2 points say P and Q of X there is associated a real number dp comma q called the distance from P to Q, and it is also called the metric. This is a function denoted by dpq. Distance means the distance between P and Q. This is also called the metric, such that number 1, there are 4 axioms, and number 1, distance from P and Q is always greater than or equal to 0 for every P and Q belongs to X. Number 2, the distance between P and Q is 0 if and only if P is equal to Q. Number 3, distance between P and Q is equal to distance between Q and P for all P Q belong to X, the metric space X. And 4, distance between PQ is less than or equal to distance between PR plus distance between R and Q for every PQR belongs to X. That means a non-empty set X equipped with the distance function, or we call the metric, is called the metric space. And what is the metric or the distance function? So we can write any function with all above mentioned properties is called distance function, or sometime it is called metric. That is why it is called the metric space. Axiom 1 states that the distance between any two points of X is a non-negative real number. And second axiom states that if any 2 points coincide, then the distance is 0, and if the distance is 0, the 2 points are the same. That is, if PQ is equal to 0, this implies P is equal to Q, and conversely, if P is equal to Q, this implies the distance between P and Q is 0. That means that if the points coincides, the distance between the 2 point distance is 0. And the third one, this property is known as symmetric property. That means the order of the point doesn't matter. That means there is no direction of these 2 points. That means suppose it is a space X, we have any 2 points P and Q. If we measure the distance from P to Q or Q to P, the distance remains same. So that is why the distance between P and Q is equal to the distance between Q and P. This property is known as the symmetric property. And fourth is the very well known property. This is called triangle inequality. Fourth property is called the triangle inequality. Frankly speaking, the sum of, suppose it is a triangle A, B and C, the sum of any 2 sides of a triangle, suppose the point is P, this point is Q and this is R, the sum of the length of any 2 sides of a triangle is greater than or equal to the third side. That means AB plus AC is always greater than or equal to BC, and this AB is nothing. This is the distance from A to B. The points are P and Q, so we can write with the definition of the distance function, the distance from P to R plus the distance from A to C, that is RQ, is always greater than or equal to BC. That is the distance from P to Q. This is called the triangle inequality. And now suppose the point R is on the line BC. This is P, this point is R and Q. Then this inequality becomes the equality. That means the distance between P and Q, this is the distance between P and Q, distance between Q and R. So if we add distance P and R plus the distance from R and Q is always equal to the distance from P to Q. When the points occur on the straight line, we always get the equality. Let's see some examples on the metric space, and one of the most important example on the metric spaces are the Euclidean space. Euclidean space, that is RK spaces, RK, and especially R1, R2 complex plane, R1 the real line, or in general RK, and the metric is defined as the distance between x and y is equal to mod x minus y for all x and y belongs to the Euclidean space RK, and this metric is known as usual matrix on the Euclidean space. Usual metric. Now example number 1. Let R denote the set of real numbers the function d from R cross R to R and defined as the distance between x and y is equal to mod x minus y for every x and y belongs to R. Is a metric on R. Now we'll have to prove this given function is a metric on R. To prove this, we will have to satisfy all 4 properties. Then we can say that the usual the function or the usual metric is this function is a metric on R if it satisfies all 4 properties. Now let's start. Number 1, we have mod x minus y is always greater than or equal to 0 for every x and y belongs to R. This implies, by the definition of the function, we can write mod of x minus y is denoted by dx comma y is greater than or equal to 0 for all x and y belongs to R. So the first property holds, that is the positivity. Number 2, we have x minus y is equal to 0 whenever x minus y is equal to 0 whenever x is equal to y. This implies d of x comma y is 0, the distance between x and y is 0 if and only if x is equal to y. We have if and only if condition in this property and we have proved. Now the third one is symmetric. Since we know that mod of x minus y is equal to y minus x, mod of y minus x for all x and y, the reason is we know that mod x is always equal to minus time mod of minus x. This implies d of x y, the distance between x and y, these points, is equal to the distance between y and x. So the third property holds, Now the fourth one, the triangle inequality. Let x, y, z belongs to R. So we have mod of x minus y is equal to mod of x if we subtract a point z and add the same point in the mod. This is always less than or equal to mod of x minus z plus z minus y, and by the definition we can write the distance between x and y is less than or equal to distance between x and z plus distance between z and y. Hence we can say that this implies D is a metric on R, and therefore we can say R equipped with D, and D is defined as above, is called metric space. Next example, and this is also very important, discrete metric space. Discrete metric space. Let X be any non-empty set. The mapping D from X cross X to R and defined by dx comma y, the distance between x and y is 0 if x is equal to y and 1 if x is not equal to y. This is called the discrete metric. Is a metric on X called the discrete metric on X. Now the proof. Now we shall show that the mapping D satisfies all four properties as we have mentioned in the definition of the metric space. Now the first one, by the definition of the mapping, we have either the distance between x and y is 0 or 1. In both the case, we can see that the distance between x and y is always greater than or equal to 0 for all x and y belongs to X. So the first property holds. Now the second one, if x is equal to y, then by the definition of D, we have D of x comma y is equal to 0. We know that if x is equal to y, then the distance is 0. So if x is equal to y, so the distance is 0. Now conversely, if distance between x and y is 0, then we must have x is equal to y. For if x is not equal to y, then by the definition of D, if x is not equal to y, this is equal to 1. The distance between x and y is equal to 1. This is the contradiction because we assumed, our hypothesis is the distance between x and y is 0. Suppose if possible x is not equal to y, then by the definition of this function, the distance between x and y is 1. So our assumption is wrong. We can say that we must have x is equal to y. So we have proved the second property. Now the third one, that is the symmetric property. Third, symmetric property. If x is equal to y, then dxy is 0. This is equal to d of yx. So in this case, if x is equal to y, the third property holds, the symmetric property holds. If x is not equal to y, then by the definition we can say that dxy is equal to 1, and this is nothing but dyx. So in this case, when x is not equal to y, we can say that this property is again holds. So for every x y belongs to the set X, we have dxy is equal to d of yx. Third property holds. Now the fourth property. The fourth property is the triangle inequality. Suppose x, y and z, any 3 points of x. If x is equal to y, by the definition we can say that d of xy is equal to 0, and also d of xz is greater than or equal to 0, and d of zy is greater than or equal to 0. This implies d of xz plus d of zy is greater than or equal to 0. Now if first case, if x is equal to y, the property holds. Because d of xy is 0, but d of xz plus d of zy is greater than or equal to 0, so d of xy is less than or equal to d of xz plus d of zy. Third property holds in this case when x is equal to y. Suppose if x is not equal to y, then d of xy is equal to 1 by the definition. So in this case, z is different from at least one of x and y, and hence at least one of x and z, d of xz and d of zy must be equal to 1. Must be equal to 1. Any of them or both. Because x is not equal to y, then there are two cases. Either x is equal to z but not equal to y, or x is not equal to z but z is equal to y. In both the case, or we can say x is not equal to z is not equal to y. There are three cases, but in all three cases we must have at least one of them is equal to 1. That means we can say that d of xy is less than or equal to d of xz plus d of zy for all x, y, z greater than x. Suppose in this case x is equal to z but not equal to y, because x is not equal to y. They cannot be equal. X is equal to z is equal to y will never comes in this case, because x is not equal to y. Suppose x is equal to z but not equal to y, we get 1 here. So this is equal to 1 plus 0 plus 1. So we get 1 is equal to 1. So the property holds. Suppose this property holds, that means x is not equal to z but equal to y. In this case we get 1 here and 0. Z is equal to y. By the definition we can say that the distance between z and y is 0, but x is not equal to z. The distance between x and z is 1. So 1 is equal to 1. And the third case, if x is not equal to z and z is not equal to y, we get 1 here but 1 here plus 1. So 1 plus 1 we get 2. This property again holds. So the fourth property holds. So we can say that D is a metric on X. We can say that D is a metric on X. Now let's take another example. Example number 3. Let X be the set of all real valued bounded continuous functions defined on the closed interval 0 and 1. We defined a norm. Of a function f by norm of f. This is a symbol of norm. Norm of f is equal to integration limit 0 to 1 mod of fx dx. Let D be a mapping from x cross x to R defined by D of x comma g. F and g are two functions of x. This is space x. This is defined as norm of f minus g, and this is equal to, by the definition of norm, the integration limit 0 to 1 mod of fx minus gx dx for every f g belongs to x. Show that D is a metric on X. In this case, the points of this space are the functions, and since all the functions are bounded and continuous, therefore Riemann's integral exists. Now we shall show that the mapping D satisfies all four properties or axioms of a metric on X. Let f g h be any arbitrary elements of X, and the elements are function, and the functions are bounded and continuous. Number one property, we have mod of fx minus gx is greater than or equal to 0 for all x belongs to the closed interval 0 and 1. This implies the integration from 0 to 1 mod of fx minus gx is greater than or equal to 0. This implies, by the definition of D, we can say that the function of f and g, the distance between x and g, the functions d, f, g is greater than or equal to 0 for all f and g belongs to x. So the first property or axioms holds. The second one, we will have to show that d of f and g is equal to 0 if and only if f is equal to g. Functions, if the functions are same, then this is equal to 0. If f is equal to g, then fx is equal to gx for all x belongs to the closed interval 0 and 1. This implies mod of fx, or we can say that fx minus gx is equal to 0 for every x belongs to the closed interval this implies we can write mod of fx minus gx is equal to 0 for all x belongs to the closed interval. This implies the integration from 0 to 1 fx minus gx dx is equal to 0. Hence, by the definition we can write d of f and g is equal to 0. So if f is equal to g, we have proved this is equal to 0. Now conversely, let d of f comma g is equal to 0. We will show that f is equal to g. So we have d of f and g is equal to 0. This implies in integration from 0 to 1 by the definition of the function d. Integrate mod of fx minus gx dx is equal to 0. This implies we can write limit x tending to a mod of fx minus gx is equal to 0 for all a belongs to the closed interval. This implies limit x tending to a fx minus gx is equal to 0. This implies limit x tending to a fx is equal to limit x tending to a gx is equal to 0. For all a belongs to the closed interval 0 and 1. This implies f of x is equal to gx for all x belongs to the closed interval 0 and 1, since f and g are continuous functions on the closed interval 0 and 1. So this implies f is equal to g. If fx is equal to gx for all x, we can say that f is equal to, functions are same, hence we have proved if d of f and g is equal to 0, this implies f is equal to g. Now the third property, symmetric property. D of f comma g is equal to, by the definition we can write mod of fx minus gx dx is equal to 0 to 1 mod of gx minus fx dx. This is nothing but d of g comma f. So order doesn't make any difference. D of fg is just same as d of gf. Now the last property, we will have to show the triangle inequality. Now we have d of f and g, this is equal to norm of f minus g. This is equal to, as we defined in the question, 0 to 1 integration 0 to 1 mod of fx minus gx dx. This is equal to integration 0 to 1 mod of fx. If we add and subtract the same function, it will not affect the answer of this integral. This is less than or equal to 0 to 1 mod of fx minus hx plus mod of hx minus gx dx. This is equal to integration 0 to 1 mod of fx minus hx dx plus 0 to 1 integration 0 to 1 mod of hx minus gx and dx. This is equal to norm of f minus h plus norm of h minus g. This is equal to, by the definition of the function, we can write d of f and h plus d of h and g. Thus the fourth property also holds. This implies d of fh is less than or equal to d of fg is equal to fh plus d of hd for all f, g, h in x. So we can say that D is a metric on x. And thank you for watching this video.